Now we will move into one of the most important applications of the concept of force on a current carrying conductor, and that is our motor. Electric motor is the most important application, and we are surrounded by electric motors, right from a toy to your water pump to your generators. We are using electric motors. Now, what is an electric motor? A motor is an electrical appliance that converts electrical energy to mechanical energy. We saw in the activity that when a current carrying conductor is placed between the pole pieces of a horseshoe magnet, what happened? Due to the interaction between the magnetic field around the aluminum rod and the magnetic field due to the horseshoe magnet, there was a force that was experienced by the aluminum rod, which made it to move. That means your electrical energy is getting converted to kinetic energy, right? Mechanical energy. Energy possessed by virtue of motion is kinetic energy, and kinetic energy is part of your mechanical energy. So using the concept of force on a current carrying conductor placed in an external field, what have we achieved? We have converted electrical energy to mechanical energy, and that is what precisely a motor is going to achieve for us. So that's a motor, but please understand that this is not the principle of working of a motor. What does a motor do? A motor simply converts electrical energy to mechanical energy. But what is the principle of working of a motor? Principle of working of an electric motor. What is the principle? We just saw. Now, what is the principle? The principle is when a current carrying conductor is placed in an external magnetic field. I'm going to repeat this. You also keep repeating it because the concept is very, very important. Is that clear? And once we are going to understand this concept, we are going to understand the working of a DC motor, right? Now, what is going to happen when a current carrying conductor is placed in an external magnetic field? It experiences a force. It experiences a force that results in the motion of the conductor. It experiences a force, and not just any force. Please get that very clearly. It's not just going to experience a simple push or a pull. It's going to experience a rotating force. And in physics, we have an amazing word to denote this rotating force, and that's called torque, right? What's a torque? You have been applying torque many a times without your knowledge that that is what is called torque. For example, every day, n number of times we open a door, close the door, right? And the door moves about its hinges in an arc. An arc is circular, right? It's a part of a circle. So that's rotatory motion about an axis of rotation. So any moment you're going to now try to push a door or pull a door, right? You put in your mind that you are applying a torque. When you are going to spin a coin, right? When you're going to convert a flat cylinder to a sphere by giving it a twist, a spin, your fingers actually give it a twist, right? What are your fingers doing? Your fingers are actually providing a torque to the coin. That's a rotating force. So when a rectangular coil of a conductor is going to be placed in an external magnetic field and current is going to flow through it, due to the interaction between the magnetic field due to the current carrying conductor and the magnetic field in which it is going to be placed, the conductor is going to experience a rotating force. Now I'm going to show that to you in a very short video, right? So this is what is the video that I would like you to see now. This is actually the setup of a DC motor. You see the pole pieces of a very strong magnet. Pole pieces mean north pole and south pole of a magnet, right? So you have it, and in between that you have a rectangular coil of wire. We are seeing only one turn of such wire, and this rectangular coil is what we call as the armature. The armature is basically the rectangular coil of wire. Now this rectangular coil of wire is connected to this commutator setup. Now what is a commutator setup? I'm going to go back to the board and write a few terms which you need to look at when you are watching the video. The first one is the rectangular coil of wire, and that is what we call as armature, right? And then you are going to see the pole pieces of a powerful magnet. That means you are going to see the north and south pole. And then what are you going to see? You are going to see a split ring arrangement. Now that the technical term that we use to denote the split ring arrangement is a commutator setup, right? You will see the setup there. It's a ring that is cut in the center, so it's a split ring, a ring that is split, and you are going to see a pair of carbon brushes. Now what are these carbon brushes? Don't think of a carbon that is brittle. This is carbon in the form of a graphite, right? Why graphite? Because you know from your chemistry knowledge that graphite is a good conductor of electricity, and it's an exception amongst non-metals. So the carbon brushes are basically graphite brushes. And why do I need these graphite brushes? These graphite or the carbon brushes are going to link my armature to the external circuit through connecting wires. So there will be a DC battery. We are going to supply direct current to the motor. Is that clear? We are going to call it as a DC motor. It's a direct current motor. So these are the things you are going to look at. Please have a look at. You have to look at whether you can see an armature. You're going to see whether you can spot the powerful magnet, and you can see the commutator setup, which is the split ring, and split ring will be linked to carbon brushes. Carbon brushes will be attached to the split ring and a DC source. Right, now let us look at this video once again. Now you can see the south pole and the north pole, and you can see the commutator segment and the brushes and the external circuit which is connected to a DC source. In this case, they are showing a simple single loop. So that means we are only using a battery to power it. In other cases, you can use a bigger battery also to power it. You can see DC motors in toys, right? In all these remote controlled cars, you will see a DC motor. Smaller fans, you know, handheld fans, in all these you see a motor. Wherever you have electrical energy converted into mechanical energy, you are going to see a motor. Now, how is this motor going to work? Now, if the setup is actually going to be in this form, look at what is happening. Look at the arrow where I am moving. The positive is connected to the left side of your armature coil, and the negative is connected to the right side of your armature coil. So what happens along the left, that is along the side which is facing the south, current is moving in the upward direction. And what is the direction of your magnetic field? The magnetic field is going to move from north to south, that is from your right to left. Is that clear? To me, as I am facing the screen of my laptop now, I can see that the north is to my right and the south is to my left. Right? So which finger shows the direction of the field? The forefinger. So my forefinger is going to be in this direction, and my current, which is the middle finger, is going to show into the laptop screen. So where is my thumb showing? The thumb is showing in the upward direction for the side of the coil which is closer to the south pole. Now look at the side of the coil which is facing the north pole. Now current is coming towards me now, but the magnetic field has not changed, right? Magnetic field. So my hand will be like, this is the magnetic field and the current is going to be in my direction. Right, now I got it. It's going to be like this, right? Do you see my center finger? The center finger is showing, pointing towards me, and the forefinger is moving from my right to left. And where is my thumb showing? My thumb is pointing in the downward direction. Let's do it once again. What's happening along the side which is closer to the south pole? Magnetic field is in this direction. Do you see the direction in which I'm going to bring my hand closer? Let's see it here, right? So the field is into the board. The current is into the board. The field is from my right. This is my right to left, and the thumb is showing upward direction. That means the force on the conductor is going to be in the upward direction. So the side that is closer to the south pole will move up. And for the same reason, if I am going to keep my hand like this, you see, field is still same from my right to left. Current is towards me. So where is the direction of my thumb? Please look at that small window where I'm showing my hand. The thumb is in the downward direction. So that part of the coil which is closer to north will move down, and that part of the coil which is closer to south will move up. Right? Now look at the figure as it is going to move, when it comes to this in between part, right? The commutator will move with the coil. That means the split ring will move with the coil. At one point, the empty space will touch the carbon brushes. The carbon brushes are fixed. Please listen to me very carefully. The carbon brushes cannot move. They are fixed. Whereas the split rings will move. And there is, at one point, the carbon brushes will be touching air. Correct? When it comes to this split portion, what happens suddenly now? The armature is not getting any current. At that point, the armature will be exactly perpendicular to the field lines. So what will happen? There will be no current flowing through the armature. There will be no magnetic field. There will be no rotation. And hence, due to inertia, because it cannot just stop, right? It cannot just stop. Any moving body just cannot stop. 9th standard physics. So what will happen? Due to inertia of motion, it will move a little bit further. It will tilt. And because of the tilt, it will fall down flat. The moment it falls down flat, what will happen? The connection is restored again. Current starts to flow again. But what will happen to the direction of flow of current? What will happen to the direction of flow of current? The direction of flow of current will change, right? This particular arm, which was initially closer to north, will now be closer to south. And because of the direction of the current, that arm will move up. That means the arm which moved down will move up, and the other one will go down. This process will keep continuing as long as there is a continuous supply of direct current. Now look at the video, what happens. The current is going to flow. In this, it is flowing down, and in the other arm, it was flowing up. So what will happen when the switch is going to be put on? The magnetic field of the current carrying conductor, see, do you see the current is moving up in this arm, and in the other arm, the current is moving down. So if I am going to apply Fleming's left hand rule, what is going to happen? Do you see the magnetic field? Do you see what is happening, children? Let me pause at a point. Okay, let's move a little further. I'm unable to stop it properly. Do you see this, children? I just stopped. It slightly moved. Do you see actually at this position? At this position, let's try slightly moving it back. No. Yeah, that's right. Almost there. You can see at this point, the current is not touching actually the conductor, the commutator. It is airy in between. Do you see that, children? So what's going to happen now? And do you see that the coil is exactly 90 to the field lines? So what's going to happen in this case? Because of inertia, it will fall down and move, fall down and move. And this rotation will continue to happen as long as there is current in the supply of the external circuit. And this is how a DC motor is going to work. Okay, so we will close today's class with this because my connection is getting a little poorer. So we will meet with you with further, explanations on the DC motor in the next class. Till then, stay safe.